AC applied to inductor. So same case we have to prove in this also. We have to apply the AC alternating current to inductor. We already know about inductor. Inductor means it consists of a coil which wound in the form of a helix. So such coils we have to take and we have to apply the AC and we should see what is the equation for voltage and we should also see the equation for current and also we should see the phase difference between current and voltage. That is what we have to understand here. Yes, let's take the source inductor of inductance here. Inductance is L here. V is equal to Vn sin omega t and this is the current. And instantaneous values of, let me directly get into the this derivation. Our intention is to see the phase relation between the current and voltage. So to prove that we should derive equations for current and voltage. Let's see. Instantaneous voltage of AC source is V is equal to Vm sin omega t. V is equal to Vm sin omega t. Now let us apply KVL to this circuit. Apply KVL to the loop. Applying KVL to the loop. How to apply? So whatever the potential developed here, that is equal to the potential across this inductor. Okay. How to write? Let's write. Summation of E is equal to 0. That is according to the KVL. So V minus L into di by dt equal to 0. Right? Why I am putting minus is it is from the Faraday's law. And Polarity inducement is given by Lenz's law. L into di by dt. This was the equation for potential developed in the self-inductance coil. It is a self-inducting coil. Potential developed across the self-inductant coil is a minus L into di by dt. That was the equation. So now let us rearrange this. Take the minus L into di by dt in RHS. That becomes L into di by dt. Now we have got this. Now what to do? We need to find out the value of current. We already know the value of I. So to find out this, let us rearrange di by dt. Take the L to the other side, and let's substitute the value for V. Take the L to the LHS, substitute the value for V. I am directly writing like this: di by dt, which is equal to V means Vm sin omega t. So Vm sin omega t divided by L is like, because we are taking that from RHS to LHS. Vm by L into sin omega t. This is the instantaneous values of current that is going through that circuit. Instantaneous means at a very short interval of time there is a current in that circuit which is equal to Vm by L into sin omega t. Now we wanted to find out the total current through this circuit. What to do? We have to integrate this. With respect to what? With respect to time. Because the current is varying with respect to time. That's it. So integrating with respect to time. See, I am writing like this: integration of di by dt with respect to dt. So if you integrated this, what you get? You get current. You get current. What is the value of di by dt? You know it. di by dt is equal to Vm by L integration of Vm by L sin omega t. Okay, Vm by L sin omega t. Now here, which is a constant? This sin omega t, Vm by L, it is a constant value. L is inductance. V is a peak values of voltage. It is also a constant. Which is a variable one? Omega t angle is a variable one because it's an alternating one. That is why it is a variable. Yeah. What to do? I is equal to Vm by L. Or take it outside. And sin omega t, integration of sin is minus cos omega t, and we have to integrate this omega t which divides this, so that is why we should write Vm divided by omega, or I can directly write minus cos omega t divided by omega. Okay, that is equation. Omega plus some constant, because it is a method which is involved in the integration. We should write some constant there, and that constant doesn't contain the term t, because this is a whole expression is equal to I. Okay, so I is always dependent on time, because I is equal to dq by dt. So current doesn't exist without the time. You cannot define it. That is why we will write constant here plus constant, and that constant is independent of. See, this is a way of doing the integration. We should have write a constant here. We should simply write constant, some constant value. But we will neglect this. Why? Because I told you that current is dependent on time, and there is no current which is independent of time. That is why we will neglect some constant. We are not adding that constant into this equation. So Vm by omega L into minus cos omega t. So Vm by omega L, you can write this as minus cos omega t can be written as sin omega t minus. Okay, this is we are writing minus cos omega t can be written as sin of omega t minus phi. Now here Vm by omega L is there. See, I am writing here omega L. I am replacing this as XL. XL means it is known as a inductive reactance. I am repeating, inductive reactance XL, which is equal to omega L. Inductive reactance means it is nothing but resistance, but it is in the case in the inductor. That is why it is called as an inductive reactance. Then what is an inductive reactance? It is in resistance. So it is a resistance offered by the inductor to the current flow through itself. It is called inductive reactance. So Vm by XL into sin of omega t minus phi by 2, and I is equal to Vm by XL. I told you that is nothing but resistance. That is why the unit of this inductive reactance is ohm itself, because the unit for resistance is ohm. So Vm by XL into sin omega t minus phi by 2, I can directly write this as Im into sin omega t minus phi. So where Im equal to what I have written, Vm by XL is the current amplitude, and XL is called as an inductive reactance. XL is equal to omega L is the inductive reactance. Now, so inductive reactance means it is opposition offered by the inductor to the current flow through itself. That is why the unit of inductive reactance is same as that of the resistor. Hence, the unit is ohm. Now, here Im means it is a peak value of current. It is given by Vm by XL. Yeah, let's write. What we have to do? Yeah, sorry. Here V is equal to Vm sin omega t. I equal to Im sin omega t minus phi. Now what is our intention? We have to see the phase relation between current and voltage. We should mainly focus on angles. See, in the place of V and Vm, here we have I and I. In the place of sin omega t, here we have sin omega t minus pi by t. If you look at these equations, particularly if you concentrate, focus on the angles, these angles are not same. Here it is omega t, here it is omega t minus pi by t. So there is an angle difference of how much? It is pi by t. That is why there is a phase difference between the voltage and current in the pure inductive circuit. What is the phase difference? It is pi by t. Okay, it is pi by t. So can we say which quantity leads, which quantity moves forward, which will be backward, which leads, which lags? We can say this. See here, V is growing sin omega t, but at the same time, I is sin omega t minus pi by 2. So that which is leading, which is moving forward, V is moving forward. Current is a lagging one because whenever the voltage reaching to angle of omega t, the minus of omega t is reached by the current. So the current is in the back of this voltage. That's why voltage leads in the inductive, pure inductive circuit, or you can say any one of the sentence you have to use, or you can say the current lags behind the voltage in the pure inductive circuit. So this is the understanding from this expression. Okay, once the current reaches to maximum value, at the same time, current will not be reached to that point. It will yet to come to that point. This is the mean. You can understand when I draw the phasor diagram. Now what we have to do? We should draw the phasor diagram and we should see the phase relations. We already know it, phase relation. There is a phase relation. By how much of angle? It is pi by 2. Phasor relation. Phasor diagram. Phasor diagram. Let's what we have to take V or I along this axis, omega t along this axis. So voltage leads, current lags. See here. This is 0th one. Okay. So when the graph reaches to this point, this is the peak value 100. So the angle covered by this is 90 degree. Whenever angle covered by this 90 degree, by the curve of voltage is 90 degree, then the current curve should be back to this by the angle of pi by 2. I hope you understood. If the curve of voltage reaches 90 degree, the current, the angle reached by this should be 0 because it should be an angle of pi by 2 back on this. So that graph will look like this. Okay, this is the graph of current. So see here. Let's say 2 points. 1 point here, another 1 point here. Okay. Okay, now see here. Look at let it be that points. I'll explain. So here this angle is 0. So once the angle by the curve which represents voltage is a 0, but this is the graph of current which yet to reach the value 0 here, right? See here it takes this time to reach the value 0. So once the value of current reaches to 0, the voltage already reached 90 degree. See? 90 degrees. So there is a phase difference of how much? This pi by 2. So voltage is leading, it is lagging. This current is yet to reach the value of 90 degree. Once the current is reached 90 degree, at the same time, voltage is reached to 180 degree. So phase difference of pi by 2. Yes. Now, so let's take the 2 points. So see here. See, this is coming in which axis? Which quadrant? It should be falling fourth quadrant. Now we are taking this at the same time, at the same angle. So we have to draw the phasor. So this is a phasor. See, angle here is omega t, and which we should lie in fourth quadrant. You can see this is in the fourth quadrant. So that this angle is, what is that angle? Omega t minus pi by 2. You can clearly understand here. See here, this whole angle is 90 degree. Part of which is omega t. Remaining should be omega t minus pi by 2. That is what. Okay. This is the voltage phasor. This is the current phasor. Values of that. You can write the value V. You have written V is equal to Vm sin omega t. I equal to Im sin omega t minus 1. So from the phasor diagram, what we can understand is current lags pi by 2 by the voltage. So there is a phase difference between current and voltage by an angle of pi by 2. So this is the understanding from this phasor diagram. Now let's we have to see what is the power loss, any power dissipation or any power any power dissipation there in this pure inductive circuit. Let's see it. And I'll draw this again. Yes, okay. We can understand the power with the help of the diagram. I already explained to you in the for the previous case when the resistor was connected. In the same way we can calculate the power in this diagram also. I told you that the power can be calculated voltage into current. See here, this is the power. Okay, see. In this case, the value of voltage is positive here. Okay, value of voltage is positive, but the value of current is negative one. So positive and negative values of current and voltages, if you multiply, you get minus negative P you will get. Here, if you take this parts, previous parts, okay, this is our it would be this would be its previous part one. Here you will get positive one. Why? Because see, this is the curve for voltage, this is the curve for current. Both are negative here in the negative axis. If both are negative, minus and minus, it becomes plus. That is why power here will be positive. That is why if you look at this part, this is where power it has absorbed. There is a power. Okay, power is absorbed by that device. If you come here, power is negative. Power is decreasing. Okay, value of power is negative 1. Negative 1 means decreasing 1, which is very less. Means the energy is releasing to the system itself. Here it has absorbed the power. Here it is releasing the power. It is absorbing the power, releasing the power. So what will be the power loss? There will be no power loss because it is absorbing some quantity of power. It is releasing the same power. So there will be no power loss. Again, if you come to this part, you will get negative. If you come to this part, again it will be plus because it is a positive value of voltage, positive value of current. Both are positive. This should be positive. Here, if you come to this is over. If you come to this part, again this is a positive and this will be negative because these are negative, negative, minus, minus, plus. Again it is minus. So here positive, negative, positive, negative. It goes on like that. Yeah. So that is why there is no average power over one complete cycle in the pure inductive circuit. But there is a power. There is an instantaneous power, but average power over a one complete cycle is 0. So power dissipation is also 0 here. That you understood from that. Power supply. Power supply to the inductor is P is equal to V into I. That is right the equation for V and I. V is equal to Vm sin omega t. I equal to Im sin omega t. Sorry, sin omega t minus pi by 2. So that is minus cos omega t. So here I am putting negative sign. Vm into Im minus of Vm into Im sin omega t cos omega t. So that is sin 2 omega t. That is sin 2 omega t. Sin 2 omega t divided by 2. Yeah. Divided by 2 sin 2 omega t. Sin 2 omega t is equal to 2 sin theta cos theta. Or sin 2 theta is equal to 2 sin theta cos theta. Take the 2 here. Sin 2 omega t divided by 2 which is equal to sin theta cos theta. Okay, this is the formula which comes in trigonometry. Okay, take the 2 here so that you will get like this. Now this is instantaneous power, average power over a cycle. Average power over a cycle is average power. You have to average this. Vm Im by 2 into sin omega 2 omega t. See here, we have a sin 2 omega t is there. Value of 2 omega t over a complete cycle 360 degree. Sin 360 it is equal to 0. That is why P bar 0 in the pure inductive circuit, which is the average power over a complete cycle. So there is no power loss in the pure inductive circuit. And you can represent this equation with the help of this one, IRMS. You can substitute the value for IRMS here. So in that way also you can write the value for this. You can modify this equation. So this is about the AC applied to your inductor. So this is the explanation about this. So from this, what we have understand is there is a phase difference between current and voltage, which is 5.